Hi, I'd like to show you how to bicolor a tree. Okay, so that's another common trick that shows up in programming contests. Before we talk about trees, let's talk about bicoloring and bipartite graphs. So graphs are more general than trees, right? Graphs can have any number of nodes, any number of edges. Trees, on the other hand, um, have exactly n nodes, n minus 1 edges, and connected. And they are connected. It means you can go from one to all the others. That's a tree. Bicoloring means to assign one of two colors, right? So, for example, in this here, this graph is said to be bicolorable because every one of these nodes can be assigned either uh, red rather, or blue, and all the edges in that graph, if they exist, always connect um, a red and a blue node. Okay, so any edge, no matter which one, has that property. It's not that all nodes are connected, but any nodes that are connected in this way. That is referred to as a bipartite graph. Very often we draw those bipartite graphs by sorting all the red nodes on one side here and having all the blue nodes on the other side or using some other color. But that is just a way to arrange them, right? So the property is independent of it. Now here in this particular problem, we want to look at how to assign a coloring to a graph and specifically a tree that has this bicolor property, right? So if we let's say if we had a let's not use that. Um, if we just to make up a really small example, if we had a tree that looks like this, then we may decide to color this tree as follows, right? We may start here and maybe here assign the blue color to this. Then we would need to assign a red color to this, blue to this, blue to this, and then again red to this. And of course, we could have done the opposite as well, right? So this it could have been the other way around. Now, in order to perform this coloring assignments, what we have to do is we have to visit all the nodes in that particular graph or tree. And so we need to do a graph traversal again. Now, one question is it always possible to bicolor a, a, a graph or tree? Okay, so first of all, it is possible to bicolor it if the graph is bipartite. In fact, those two things are pretty much mean the same thing. In the general case, of course, it is not always possible. I'll just give you two examples, right? So here's one graph. Here, if the graph is like this, in this case, then we start here, we would assign maybe red to this, but then we would be forced to assign blue to this one and forced to assign blue to this one. And then here we would have an edge that would not work, right? It doesn't connect two of the different colors. So this graph is not bicolorable. Let me show you another example of a graph that is. So if you had this graph here, then because we could bicolor this by assigning red here and assigning blue here and here. Now, so this is about general graphs, but what about trees as special graphs with n nodes and n minus 1 edges? Turns out trees are bipartite graphs. They're always bicolorable. All right, so now the question is how to find such a bicoloring and how to actually code that. Okay, so to that end, let me show an example problem, and this example problem was called molecule. And in this problem, essentially, the insight was that you needed to find such a bicoloring. So in the interest of time, I will skip over the graph representation that I had discussed previously in the video and show you just the algorithm. Okay, but to mind you, so this is a standard setup, adjacency list arrays, n nodes, initialize the adjacency lists, and then we're reading the edges, and those are again here undirected edges, in this case for a tree, correct for the indexing, and write them into those adjacency lists. And then once we have found a node coloring, we want the node coloring to be node color. Okay, this is like true or false. Um, if node I is red or blue. And in this particular problem, we needed to output 0 or 1 in this case. So at this point here, we have the graph ready. We want to bicolor and typically implement that recursively. So bicolor, we can say bicolor, let's just say call it bicolor. I can start at any node, right? So this works starting at any node, so why not start at node 0? And then I need to pass in the color that I want node 0 to be, and I just pick one value here, and that value is, let's say, false. And I'm gonna pass in a third parameter. I want to explain in a second here, negative 1. So the bicolor function takes two arguments. One is the node that we start bicoloring, then the color, and then a third argument. And this is the one, as we'll see, that we came from. We call this the parent argument. I'm sure how to pass that in. All right, so what does coloring entail? We certainly need to set the node color of that node to the color that we're currently assigning. And then we need to make sure that all the neighbors of this node here are being assigned the opposite color, and also that um, that that we recurse that, right? So we would call it with we would pick a different color. Okay, so now let's stop here for 1 second. Okay, so what would happen if we did just this? Okay, so we would start with one node in a tree. Okay, let's say if our tree looks like this. When we start here, and then maybe there are other nodes here. So we would start here. This would be our u. We would call this function, and we would now explore the neighbors of this node. So we would recurse this direction, great, this direction, great, this direction, great. But actually, because of the way undirected graphs are represented, there would be another entry in the adjacency list of u here that would point back. And of course, we don't want to go back because this is where we came from. And so we need to remember where we came from and simply skip that. Okay, so we remember where we came from, which is u, and we skip that, meaning that we only traverse v if it is not the parent. And that's already the entire algorithm. Okay, let's see if that works. And let's try it out on the actual problem to make sure we didn't miss anything. And voila, it seems to work. Okay, so a very simple algorithm to perform a recursive DFS of a tree. Okay, so tree means connected graph, n nodes, n-1 edges. Okay, point out that this trick here did not require that we maintain it does not need a marked array, okay? Because we had some other clever way to make sure that we would not return from a node to its parents. And also because it is a tree, okay, there are no cycles. Okay, in fact, that's equivalent being connected in a tree and not having any cycles. And you can also see how this algorithm would be easy to extend if you did have a graph, just to mention this. So in that case, first of all, you would need a marked array again. But in that case, then you would also need to encounter a situation where you are crossing along an edge here that reaches a node that you may have already seen. And in this case, you need to say, well, so to show this, let's say if you start with one node, you go to another node, and I'm talking about general graphs here, not trees, and then a node here and a node there, and a node here, and maybe we have nodes this way, And suppose we started this one here with traversing this, right? So then this one would be blue. We go down here, make this one there. Then we would probably put this one blue, and then here we would be traversing this. And then as we go down this edge here, we're going to say, okay, we've seen this already, yes, but it's okay. And then we would go down here, mark this one. But when we go back here, okay, let's say, have we seen it? Yes, but that does not work because they've both been assigned and they're both red. Okay, so the algorithm can easily extend it to do that, but we do not need that for trees because we know that trees are bipartite, they are bicolorable, bicoloring exists, and this is the code to easily find it.